the presentation is going to be slightly different. There's going to be there's less applications and more in a method that we've been working on. I'll definitely go into some example applications in the end. So I'll be talking about embedding regression, and I should say this is joint work with Arthur Sperling at NYU and Brandon Stewart at Princeton University, and of course it has benefited a lot from comments, including from Jesse and many other people. My slides don't seem to be. Here we go. All right, so I'll get started with the thought experiment to sort of set the scene. So suppose that you had never heard of the word migrant before, right? And you encountered the word for the first time reading Fox News headlines, such as the following, where the word migrant appears in the context of such words as drug cartels, open borders, security crisis, surge, and so forth, right? So the question is, what do you infer about the meaning of the word migrant from reading these headlines, right? Now, suppose that instead of Fox News headlines, you had encountered the word for the first time reading CBS News headlines, such as the following, where the word migrant appears in the context of such words as refugees, children, family reunions, desperate, asylum, and so forth, right? Again, the question being, what do you infer about the meaning of the word migrant from these headlines? And importantly, how does that differ from the inferences that you'd make having heard the word for the first time reading Fox News headlines, right? So this thought experiment helps illustrate a broader research objective or task that we have in political science. And I'd argue, and I think the projects that were just discussed show, I'd argue sort of a broader research objective in the social sciences, which is that we want to quantify systematic differences in meaning across groups and time and get some sense of the associated uncertainty, right? Now, I should clarify before continuing what we mean by meaning. We're building on what is called the distributional hypothesis, and this is common to most of the most popular methods in text as data, which essentially, in sort of simple terms, what distributional hypothesis states is that we can learn something about the meaning of a word from the contexts within which it appears, right? So just as we were doing in the thought experiment, I was saying, the word migrant appears in the context of such words, and we were learning something about the meaning of those terms from these two different news sources. That's essentially that's the basis of most of the more popular text as data methods, from those that you probably already know, like topic models and latent semantic analysis, to the more recent, transformer-based models that use also context in a slightly different way, but also rely on context. So that's what we mean. When I say meaning, it's essentially talking about meaning defined by the context of the words surrounding the term of interest. So returning to our problem at hand, essentially what we want is something like semantic regression, right? That we can run a regression, something like the typical equation that we know, where we get some sense of the expected meaning of a term, for in our example, migrant, conditional on some set of covariates. For example, in the case of the thought experiment, it was conditional on, say, the news source, but it can be conditional on any sort of group level covariates or any sort of time varying covariates, right? Time covariates. We're going to restrict this method to indicator variables, so to binary indicator variables, but it can apply more broadly. I should clarify also here, the expectation is being taken. So what's the data here, just in case, to clarify, the data is all those instances of the terms that we're looking at. The data, for example, in this case of migrant, is going to be all those mentions of the word migrant in those set of headlines, right? So that's sort of the individual level data that we have. The problem or the challenge is that this presupposes we can numerically represent each individual instance of the target term of the word of interest, in our case, migrant, in our corpus, in a way that captures the variation in meaning, right? In a way that captures that variation in the context within which it appears. And we can represent this numerically to be able to run this regression. And that is generally pretty challenging to do, right? That's not straightforward. So what we do in this work is that we leverage pre-trained word embeddings. For those that aren't familiar with word embeddings, these are dense numeric vector representations of words that essentially map words onto a multidimensional space wherein two similar words are going to be closer together in that space than words that are not so similar, right? So the distance in this space is going to be a function of semantic similarity, right? And pre-trained word embeddings are essentially embeddings of these numeric representations that have been trained on very large data, on very large corpuses of text. For example, on the whole of Wikipedia or the whole of Google News and so forth. And so you essentially get a numeric representation of the entire vocabulary that you can use to, work with words numerically, right? The problem with pre-trained word embeddings, though, is that they were trained on a different text, presumably, than the one that you're interested in. So, for example, if Mark were to use this, his text is very different from the text that was used to train these word embeddings. And so you want to be able to adapt to the context. And that's where a recent innovation by Kodak et al., right, comes in, where they essentially show how we can use those contexts along with pre-trained embeddings to adjust those pre-trained embeddings to the local context that we're interested in. And so what we do in this work is we take that innovation, again, leveraging pre-trained embeddings and that innovation, and insert it into a regression framework that allows you to run those types of regressions that I was just mentioning, where essentially you have a numeric representation of the term or text that you're interested in, and you can regress it on a set of covariates to understand how the meaning or the usage of that term varies as a function of those covariates. And so this framework, is transparent, is very, it's not so black box as sort of many other alternative methods that are out there. It's very efficient and computationally simple. It importantly, again, allows you to evaluate hypotheses as a function of covariate effects and so forth, of covariates. It performs well, it's important, it performs well in case of rare words and small corpora, which is oftentimes what we face as social scientists. We don't always have very large collections of text, and it provides both accurate interpretable results, and it's generally much faster to run than sort of other sort of covariate-based embedding methods that are out there. I'm not going to go into the methods. Instead, I'm going to jump all the weeds and go into some applications just to show you the types of stuff that you can do with this. So suppose that we're interested in understanding partisan usage of terms in the US Congress, right? So our data here is going to be the congressional record. These are transcripts of speeches by representatives on the Senate and Congress and the House. We're interested in understanding the usage of the terms immigration, marriage, abortion, and we're going to use as essentially placebos or as a test, right? Some stop words, things that we have strong priors that shouldn't vary in meaning as a function of, say, party membership, right? Again, we're going to be using as the pre-trained embeddings, Stanford Glove 3. These are Glove embeddings, 300-dimensional embeddings. These can just be easily downloaded online. These have been trained on Wikipedia and Gigadump, I believe it is. And let's take a look at some. Oh, and the model. This is a regression model. Just the type of sort of regression equation that we know and love. Except these are going to be multivariate. So the yi here is a numeric representation of the term. So it's going to be 300-dimensional, this y, right? Which means that the coefficients, the betas, are also going to be 300-dimensional, right? A way of capturing, so when we estimate this, we're going to end up with 300-dimensional betas, very large betas. We can't visualize that easily. So what we do is we just take the norm of that, and that gives us a sense of how large those betas are. So the norm is just one, scalar. One number. And so this is what we're looking at here. We're looking at those betas, the norms of those betas for the different terms. The larger the norm, the larger the effect of that covariate on the meaning of that term, right? And so if we look at first the stop words, right, we see that there isn't much of a difference between the female or the gender and the party membership effects, the coefficients, right? There isn't much of a difference here. When we're compared to the partisan terms, we see that the effects are much larger, right, for the partisan terms. Again, as we expect a much larger effect in terms of the differences in how people use and how representatives, in this case, use these terms as a function of party membership and gender. Notice that the party membership, again, consistent with our priors, has a much larger effect than gender effects, right? The differences because of party membership are much larger. Again, arguably consistent with priors. We can also look at this in a sort of more qualitative manner, by looking at the nearest, what are called the nearest neighbors. For those that aren't familiar, again, with word embeddings, nearest neighbors are essentially looking at, so we have a representation, we're looking at immigration right now. So we have a vector representation of immigration for Republicans, and we have one for Democrats, which again captures in some way the meaning or the usage of that term for both of those groups. And what we're going to look at is the terms that are nearby those representations of immigration for Democrats and nearby those representations for Republicans. And this is what we're going to map here. In addition to that, this plot captures how much more near it is to Republicans than it is to Democrats. So if it's further to the right, it's going to be much nearer to Republicans. And if it's further to the left, it's going to be a term that is nearer to Democrats. So these are some terms that are nearest neighbors to both, are close to both representations. If we look then at terms that are much nearer to Democrats relative to Republicans, we see they talk more about bipartisanship, reform, overhaul, and so forth. I should note the congressional corpus here is during the Obama years. So this is the Democratic Party in government talking as sort of, it makes more sense about bipartisanship and reform when they talk about immigration. Whereas whereas Republicans were talking more about enforcement and well, the usual sort of the illegals and naturalization, sort of the terms that sort of we know that tend to be more referenced by Republican representatives, right? So again, there's sort of a more qualitative / quantitative in a way, capturing sort of how these terms differ in their usage. We can also use this framework to study differences over time, right? So in this case, we're going to be looking at how the meaning of empire varied, and we're comparing over this period, 35 to 2010, and we're comparing the American Congress to the British Parliament, and how the meaning of that term varies across these two groups. Here, the coefficient just captures membership to the American Congress. So it's just capturing whether the term came from an American representative or whether it came from or was mentioned by a parliamentarian in the UK Parliament. And we run separate regressions for each year. In this case, we're training our own embedding models on this. This is a very large corpus, so we can train our own embeddings model, and we use it here. And we plot the norm of that beta, right? The norm of that coefficient over time. So we see that it varies quite a lot over time. But importantly, when we do a structural test, break analysis test, we see that there's a structural break right after the Second World War, right? So if we, it sort of makes sense, but at the same time, you want to dig into the data, and that's where you go into the nearest neighbors. And when you look at the nearest neighbors, I'm going to skip this one. When you look at the nearest neighbors after the Second World War, you see that the break comes from US Congress representatives talking more about communism and the Russian as an empire, whereas the British kept on talking about the British Empire, right? And that sort of before the end of the Second World War, everyone was talking about the British Empire and Germany and Japan and so forth. After the Second World War, the British kept talking about themselves, and the US shifted towards talking about Russia and communism. And one final example of an application is Openended, right? So the two applications that I've just mentioned, we've been looking at a particular focal word. In one case, it was immigration and sort of these partisan terms. The other was empire. But you can also look at short texts. So you can embed a full sort of short text like an open-ended response and see how that open-ended response varies as a function of covariates in your survey, for example. So we're going to be looking at the ANES survey is one of the biggest political science surveys in the US, and looking at the question, most important problems facing the country is an open-ended question. And our regression model is going to be, going to have a gender covariate and then ideological covariate. So we're capturing whether you indicate that you're moderate, whether you indicate that you're conservative. And again, so here we're plotting just the norm of the coefficients. So again, we see, I'd argue, consistent with priors, that the ideology coefficient or the ideology effect is larger, and it's larger as you grow more extreme. So the more conservative is going to have a larger effect on the change in the response, right? And if we look at the nearest neighbors to dig into the results, we see that as the more conservative you go, the more likely it is that you'll mention terms like immigrants and immigration and jobs as part of the more important problems facing the country. Whereas the more liberal you were, the more likely it is that you mention terms such as racism, injustice and intolerance and so forth. So to end, just to say that we put together a software package in R. Hopefully we'll start working on a Python version soon. And you can run, if you're familiar with R, we follow the LM and GLM syntax. So you can just type your equation, for example, in this case, determine migration as a function of party and gender. And it has the options to do bootstrapping, permutation, and so forth to get the sort of the uncertainty measures and the inference side of things. Just today it was accepted in CRAN, so now you can easily download it straight from CRAN. Again, if you're familiar with R, that's sort of where all the packages are stored. And you can find the paper on our GitHub, as well as the sort of a quick guide in terms of how to use the package. And that's it. I should stop, and I look forward to comments and questions.